So the big picture of what we're talking about today is essentially getting the structure of molecules. And I'm not sure why they picked this topic, but it's in the book, so that's why we're handling it now. Now the big goal is to get these molecular shapes. Because the shape of a molecule, how it's folded, how it's bent, its angles, everything is going to interact with its properties. Now its properties mean it could be what? So these compounds are really simple, but they're really flat. So it's not a very good idea of what they actually look like in real life. Why do you care? You care because these molecules could be more like these that you have images of. These are really important molecules up here. These are like vitamins. There's some important anti-tumor drugs in here. There's some important proteins in here that your life depend on every day that's going on in your cells. How do they get these shapes? But the key is that you figure out what these shapes are, and they really help you understand the chemistry and predict how things are going. Or, I think where the real money is you find a vitamin and it does something in your body. You know that molecular shape. Well, let's modify it a little bit. Does it enhance the properties of this vitamin? Does it make it worse? Is it all of a sudden a cure for some disease? That is big money. So you figure out what these shapes are and modify them. But the point is that it all starts out with a perfectly shaped little crystal. So what we're really talking about is X-ray crystallography, because that's really the big picture of all this stuff, is how do you get these molecular shapes so you can see what's going on. And it all starts with those really nice crystals. And I was talking to an X-ray crystallographer. He says that's the hardest part, because the computer pretty much does everything else for you. But getting that really nice crystal. So what we're talking about is we're not going to generate these nice, beautiful molecular shapes of proteins. No, we're going to talk about the fundamentals of this. What are they after? What they're after in a crystal is just they call it a unit cell. And it's just repeating in space. And through X-ray crystallography, you can figure out what those unit cells are and generate these actual molecular shapes. So we're just going to talk about the simplest unit cells. But let's start out by just seeing a couple things. One is graphite, the stuff in your pencil. And then the other object there is a diamond. Both of those, Alyssa, are composed of what element? Allison. Graphite, diamonds, they're all composed of? Carbon. They're all composed of carbon. Well, one of those is so soft, allotrope is the word. I don't know if you remember that, or if we even talked about it. Just different crystalline structures of the same element. They're called allotropes. One is diamond, one is graphite. Let's take a look at these. I'll show you diamond first. There's diamond. So all these green spheres are what again? Carbon atoms, right? They're all carbon atoms. It's really compact, hard as a rock, right? You just rearrange those atoms in a different manner, and you get this. So what do you see that's differently, Jose? Yeah, this one's graphite. Graphite is one of the very few solid lubricants that we're aware of. How can this be slippery? Andromeda, how could this be slippery? And it's so slippery you can write with it, right? And this stuff just sloughs right off. Draw lines and write. You see what's going on here? This layer is just going to slide right off the other layer. That's graphite. Very different than diamond. Very different crystalline structure. So pretty much all that's holding these layers together would be what type of force, would you guess? Has a lot of area, really weak. London. Or you can also remember, if you don't remember the word London, there are two other words for it. Van der Waals and dispersion, right. So that's why it's really weak, and they just slough right off one another. So that's actually what you're writing with. If you're using a pencil, I guess. We have, I've got some salt, sodium chloride, and some sugar, right? You've held them in your hands. They're both white, but they both look like little crystalline structures. But what types of compounds were they? See if we remember this. We had these different types of compounds. Kendall, let's start with salt. These two different types of compounds. If you want to throw them all into two categories, these compounds where you had different elements combine, and you can characterize them as a salt-like compound or a sugar-like compound. The salt one starts with an I. I-O. Anybody help her? Ionic. Ionic is held together. So this is just a kind of a review. Sodium chloride. There's table salt. Held together by ions. Right? A crystalline structure of sodium ions surrounded by chloride anions. Or if you want to think of chloride anions being surrounded by sodium ions. And it's all held together by those electrostatic forces. Okay? And what's the crystalline structure? Well, that's kind of what we're going to be talking about. You'll see some pictures down here. That was salt. Steph, how about sugar? Molecular. They also started, well, how do you spell molecular? Molecular. There's also the C word. Covalent. So sugar, exact same thing. You hold it in your hand. You see, you can look at it really close. It's a crystal again. But now it's a crystal of molecules, sugar molecules. Okay, a bunch of carbon, hydrogen, and oxygen making a molecule. Okay, so we have these different types of solids, right? You've got ionic solids. You've got solids that are made up of ionic compounds, solids that are made up of molecular or covalent compounds. And that's what this little table down here below is trying to figure out. It's trying to illustrate that at the bottom of the pile, you've got molecular solids. At the top, you've got this covalent solids. And they just call it covalent network, fine. Okay. So, I don't know, we can start at the bottom, I guess. At the bottom, you have these molecular solids. Well, how do I say this? I kind of changed your chart because I thought it was kind of confusing. Molecular solids are held together by blank, but I'll get you started here, just let you see where I'm headed. Molecules, right? Molecular solid consists of molecules. So what I'm trying to help you out here with is the question like, what type of solid is ice? For example, ice is just frozen water. So ice would be an example of a molecular solid because it's composed of water molecules, right? So any solid that's composed of molecules, you're supposed to call it a molecular solid. You see, there's 1, 2, 3, 4 of them, so you got to keep all these straight. Okay. It's held together by what? So Enrique, we've got these water molecules. You make them cold enough, they start interacting enough where they're a liquid, but then you make it even colder, they're immobilized even more, turn into a solid. But what's holding this stuff together? One of the forces, right. So now we got what was the name of all those forces, though? Starts with an I. Yeah, but in general. Intermolecular. Because we may not be talking about water all the time, right? So you could, if it was water, you'd say hydrogen bonding. But it could be any type of solid. So intermolecular forces. Intermolecular forces. Okay, so you have a molecule, it's got to be molecular solid, held together by intermolecular forces. Metallic solid. Oh, Mia, we've got a metallic solid. A metallic solid probably consists of, here's the only hint I can give you, metallic. So it consists of the M word? Metals. Well, I guess you should say metal atoms, right? Metal atoms might sound better than metals since we're talking about the atomic structure here. Metal atoms. Pretty much the entire periodic table, Andrea, is what? Metals. Okay. Metallic solids are held together by, you have iron, right? Composed of iron atoms. What holds the darn thing together? You may have heard of this, but let's talk about silver, because I know that silver forms Ag+, right? Because iron forms a couple of different ones. So what they're trying to say is this is how they want you to, I can't draw 3D at all, so I'm just going to draw like 4 of these guys. There's silver. Each one donates an electron. Because it's a metal, so it should conduct what? Electricity. So there's got to be a lot of free-floating electrons in here. So there are. Each silver atom donates one. Got this ocean. They call it the sea, right? And this whole, all these silver ions in some lattice are just coated with this electron sea. So, right, this guy's positive, but look what's between there, the electron sea. So they're both pulled towards there, and that's what's supposed to hold it together. So nobody knows whose electrons are whose. You just have all these cations, and then they're just held together by, because there's electrons in between. And they're free floating, they're everywhere. That's why it conducts. So metallic solid is held together by electron sea. Isn't that weird? But that's what they believe. Things could change, but they haven't changed in about 20, 30 years, so it's probably a good model. Ionic solids consist of ions. Perfect. Right. Ions. Inessa, if I said potassium phosphate, well, that must be what type of solid? Ionic, because you have potassium ions and phosphate anions, so it's got to be an ionic solid, right? Held together by, what would you guess, Audrey? Held together by, you have all these ions. You always have cations, you always have anions held together by, I guess, opposites attract. But the way we're not supposed to say that, we're supposed to say electrostatic forces. Right? What else? Isn't that, I can't think of another word. You have a positive charge and a negative charge, they attract. Is there anything else they use besides electrostatic force? I don't think that's it. I think that's it, right? So if you can think of another one, put it in there, but that's all I can think of. Electrostatic. Plus and minus. Okay. The highest on the scale here, Bowdy, are covalent network solids. Consist of what? Covalent bond. Well, that's the answer for holding it together. Held together by covalent bonds. Okay. I think, do metals form covalent bonds? No. Metals form, I don't know, metallic bonds or electron C bonds, right? So the only thing that you're going to have covalent solids are what can form covalent bonds. What can share electrons? Not the metals, but the nonmetals. Carbon, perfect. Carbon network solid, diamond, right, consists of, I guess you could say nonmetals. I guess we should say ions, right? Or in this case, not ions, but atoms, right? Because we're talking about the very microscopic level. Okay, as you go up this scale, Kenneth, it's increasing blank strength. Bond strength, perfect. And it's kind of a poor choice of words, I think, because like the electron C, where's the bond? You know, it's kind of like all over the place. So, but that's the idea. Increasing bond strength as you go up, increasing interaction strength that's holding the crystal together. So increasing blank point. Now it's solids though. So not boiling. Boiling would work, I guess, but melting. Okay. So I don't know, maybe you can kind of see the questions that are coming up. They're going to give you a whole bunch of compounds. They're going to say list them from lowest melting point to highest melting point. So the only way to answer this is to figure out what type of solid each one is. So just remember this, what they consist of, and you'll be fine. Covalent networks, solids are always going to have the highest melting point. Anything molecular will always have the lowest melting point. Okay. Okay, so that's pretty much the majority of your homework. There's just one left. And they threw this in there. So we talked about earlier getting all these structures of these proteins or these molecules or these vitamins. And how do they do that? Well, they have these perfect, beautiful crystal structures of them, right? And that's where it all starts, with the unit cell. Well, there's some simple, really unit cells. And unit cell is just a repeating unit in the crystal. And here's the three simplest ones. It's kind of like taking a bunch of balls, dumping them in a bucket, and how do they pack themselves? So here's the three simplest ways. The first one is simple cubic. So you have a cube, and then you've got an atom. So these are supposed to be atoms. That's supposed to be one atom. An atom at each corner. And what the homework is going to do, here's one right here. They're going to say, what type of cubic lattice does gold have? So there's a lot of blah to get there, but that's the question. So the answer is going to be one of these. So how do you know which one? What you need to remember is how many atoms essentially are in each one of these unit cells. Now, it doesn't look like there's a single atom in here, but you have to add up all the parts. And like in the simple cubic. And let's change this to 1/8. 1/8 of an atom is actually inside the box, inside the unit cell, at each corner. Well, Jose, if you have 1/8 of an atom at each corner, there's what? 1, 2, 3, 4, 5, 6, 7, 8. 8 corners. How many atoms would be in this unit cell essentially contained if you add up all the parts? 1/8 at each corner. You've got 8 corners, so it would just be 1/8. Well, 1/8 plus 1/8 plus 1/8 plus 1/8 plus 1/8, right? 8 times. That would just be 1. So you have 1 atom. So that's what you need to remember. You have 1 atom. Let's see if we can see that. So here's simple cubic. And you have 1/8 of an atom inside that unit cell at each corner. With, let's see, body-centered, all they're saying is now you've got 1 in the center. He's completely in the center. So now the answer is not going to be 1 anymore. It's going to be 2. 2 atoms. And then you have face-centered. Well, let's take a look at body-centered. Let's see what it looks like here. There's body-centered. So you've got 1/8 at each corner, plus an entire atom right in the center of the whole thing. So you have a total of 2 atoms. And then the last type is face-centered unit cell. So you don't have anything in the center anymore, but you've got a half at each face. So it's hard to draw these things. You might be able to see it better in the animation, but like this guy's in the face, but only half is actually inside and half is outside. So that means you're going to have, at the corners, you've got 1 total, right? So there's 1 total just from the corners. And then you take 2 faces, and you'll get another one. 1, 2. So how many total will there be? 4. Total will be 4. Because there's another one, add up the 2 faces. You've got 6 faces. So I mean, there's going to be 3 more. Four atoms total. Let's see. Whoop, lost it. There it is. They're really jamming them in there, right? Okay. So let's see if we can answer. So the big question is, what type of cubic lattice does gold have? Your answer is going to depend on how many atoms are in the unit cell. Okay. So the question is, what type of cubic lattice? The answer is going to be one of these 4. So do you see the information they got to give you? They have to give you the number of, some way to calculate this unit cell and get the number of atoms out of it. So let's see the information they're giving us and see if we can figure it out. Gold has cubic crystals whose unit cell has an edge length of 407.9 picometers. Pico is 10 to the negative 12. Picometers. So pretty tiny. 407.9 to 10 negative 12 meters. The density of gold is 19.3 grams per cubic centimeter. From these data and the atomic mass, calculate the number of gold atoms in a unit cell. And then from that, you better get 1, 2, or 4, and then you'll figure out what type of cubic lattice it has. So really, the idea here is this. Get the mass of gold in 1 unit cell. Get the mass of gold in 1 unit cell. And then divide it by the mass of 1 gold atom. And you're going to get 1, 2, or 4. If you don't, you messed up. So you got to get the mass of gold in a unit cell, and then divide it by the mass of a gold atom. So the top part's going to be a lot harder than the bottom part. The bottom part is easy if you remember the trick to get the mass of any single atom. How do you get the mass of any atom? Oh, you're going to need Avogadro's number. That's half of it. What's the other half? Molar mass is the word, right? So we find the molar mass of gold, divide it by Avogadro's number, we'll have the mass of 1. Okay, so where's gold?
Under copper.
That doesn't help. 79, there it is. 196.97. So we'll have 196.97 grams divided by Avogadro, and that'll be the mass of 1 gold atom. Might as well finish that one, right? Calculator. 196.97 divided by 6.022 to 10 to the 23rd. Now this is good practice for you. See if you remember how to do all this on the calculator, like especially the scientific notation stuff. Okay, and if you do it right, you should get 3.27 times 10 to the negative 22. A really small number, which is good because it should be really, really small. Okay. Remember, how do you get 10 to the 23rd in the calculator? You do 6.022, then push the EXP button, and then 23 and hit equals. Okay. It work? Okay. Bottom part's done. Let's get the top part. Mass of gold in 1 unit cell. Okay. They said it has a... That's what you got to use. Because 19.3 grams, that's grams of what? Of gold, because that's the density of gold. That's the grams of gold. So all we got to do is multiply this by what to get grams of gold? Because we want grams of gold. So don't flip that 19.3 or anything. Multiply this by what, and we'll have it. What's this thing? Centimeters cubed, yeah. That's what, Megan? Volume. That's volume. Does anyone see the trick? What's that? Yeah, we can do what Anessa is saying. You can say D equals M over V, and then solve for M. That works, but that's kind of what I'm doing up here. It'll be the same thing. You can get M equals D times V, which is what we're doing. So either way works, but either way we got to get V. This might be easier because it kind of tells you, you know density, you just got to get V. Multiply this by V. V has to be in what units though? Centimeters cubed. Well, how do you get volume of a cube? Length times length times length. Well, length times width times height, but they're all the same. So it's length times length times length, right? Our length is how much? There it is. Let's just convert this to what? Centimeters, and then cube it. Okay, so we should do that somewhere. Let's write it up here. 407.9 times 10 to the negative 12 meters. Okay, how do I convert? Oh, who am I picking on here? Kendall, how do I convert meters to centimeters again? Kendall, there she is.
Okay, so we're going to multiply meters by...
The M has to go where? Help you out. The M has to go
at the bottom.
on the bottom.
And then centimeters on top.
Centimeters on top. No, slow. The reason why I want you to slow down is because this is the starting point, right? This is the starting point. M has to go on the bottom so it cancels. CM has to go on top. You have no choice in the matter. You just got to remember what number goes where. Remember the number O. I'll give you a hint. Just let me finish. The number always goes with the prefix except for everybody? Kilo. Yes. Fantastic. Okay. So she better put a number with a centi, and it's going to be 100. Perfect. We got it. We're done. We're in centimeters. So that's going to be 407.9 times 10 to the negative 10, I guess, if you're good with your exponents. Then you got to cube that number. So take 407.9 times 10 to the negative 12. 407.9 times 10 to the 12 negative. Take it times 100, and you got this answer in your calculator. Now, what's the easy way to cube it with these calculators? Hopefully, you should be bringing this calculator to class because it'll make life a lot easier with the homework. There's a button. One button. Where is it? Oh, that x to the power y always works. That would work. You could push that and then push 3, or you could push the x cubed button. And the x cubed button is orange, though, so you got to push shift first. So I think that's kind of easier because it's cubed. But which she said is work too, but shift x cubed. So I got 6.78, so I'm going to write that number down here. 6.787 times 10 to the negative 23. Okay. So take this times 19.3, see what you get. Divide it by, and that's going to be the mass of gold in a unit cell. Divide it by this mass of one gold atom, and you better get 1, 2, or 4, or we screwed up somewhere. What'd you get? Yeah, I got 4.0056 or something. Well, you're supposed to say that's what number? Supposed to say that's 4. So are you getting this? So that means in each unit cell of gold is 4 gold atoms, essentially, if you add up all the parts. So it has to be what type of unit cell? Face-centered cubic. That's the answer. 4 atoms, face-centered cubic. Did you get it to work? Audrey, you get it to work?
No, sir.
Where'd you mess up?
Well, when I first did it, I got negative 0.8. I like to the negative 0.8 instead of your negative 10, just on the converting.
Oh, well, make sure this is 407.9. It's not 4.079. 407.9 EXP 12 negative times 100. And then you'll get, I just did this in my head, I shouldn't have. If you do it, it's on your calculator. That's going to be 10 negative 10. What's that, 10 to the negative 8? If you're doing your calculator, right, I just added exponents. I was lazy. So you should get 10 to the negative 8 here, right? Cube it, and you'll get this. Okay. So the trick to doing these, what type of cubic lattice is there, you got to figure out the mass of one of the atoms, right? And then you also got to figure out from the density all the mass of that's in that one unit cell. So that means every time they're going to give you, it's going to be the exact same problem. They're going to give you the length of one side. You cube it, you multiply by the density, and you get the mass. Divide it by the mass of one atom, see how many atoms that are in there. And you'll get 1, 2, or 4 every single time. Okay. So Steph, did I lose you? Did it make sense? I was just picking on somebody. Cameron, make sense? Okay. At least you got a model to follow for the homework, right?
The answer is we have to put 4 and.
Oh yeah, I didn't write it. You have to write 4 and face-centered cubic. Because they wanted both. Okay. I think a lot of the homework, though, Enrique, is this. You might not be spending so much time on it, because once you get to figure out the trick, it won't take so long. Which of these solids do you expect to be molecular solids? Now, there might be more than one answer here. Which ones do you think? It's going to be molecular solids. That means it has to be made up of, what, Enrique? It has to be made up of? Yeah, it has to be made up of what then? The M word. Molecules. It has to be made up of molecules. Well, that means covalent compounds. However you want to remember this, right? Covalent compounds. There's only a certain area, range of elements here that will form molecules or covalent compounds. Have the sharing of electron idea in their bonds. What were they? Anything but a metal. Anything but a metal. So that means just that corner up there. Remember the staircase? We should draw on a staircase, right? Have Kenneth climb up there and draw on that staircase. Remember seeing those periodic tables that do that? So in here, Mia, which ones would be the molecules? Which ones would be the molecular solids? She says Cl2. Does everybody agree? LIBR, everybody agree? No, because BR is good. BR is good, but you got the LI, so don't do this one. Yeah, 2 nonmetals. That'll work. Is there anything else? Because cadmium's a metal. What type of solid would cadmium form? Metallic. Lithium bromide would form ionic. Arrange the following compounds in order of increasing melting point. You got A, B, C, D. List them A through D with the first letter having the lowest melting point, the weakest interactions going on in that crystal. Let's pick on Andrea. What was your final answer? What did you say? You listed what to what?
Potassium chloride would have the lowest melting point.
What type of compound is this? Potassium chloride. Does it have a metal? That's all you got to look for. Does it have a metal?
Well,
I don't know. Chlorine's way over here. Definitely a nonmetal. But where's potassium? Way over here. So K, it definitely is a metal. So this would be what type of compound? It's metallic if all there is there is the metal. Ionic. So figure out what each type of compound is here. That's a big clue, right? So she's right. This guy's ionic. What's A? Ionic. How about B, everybody? B is, to make this simple, just look for a metal. If you see a metal, do you see a metal? No. So that means this has to be molecular. Why isn't B covalent network solid? It's not it's composed, this is composed of molecules, not atoms. The covalent network solid has to be nonmetals, yes, but just atoms, nonmetal atoms. Carbon, like diamond, right? So this is a molecular solid. C is a molecular solid. Okay, molecular solids. So we've got 2 of each. Which one, Alyssa, has lower melting points? Yeah, which type of compound has lower melting points, molecular or ionic? Molecular. So we better be listing B and C first, and A and D last. So Anessa, which one did you list first then? B, lowest melting point. You have a 50-50 shot at this. Okay, now there's some thinking though here. What type of intermolecular force is going on? This is pulling it out of the homework from the last class period. It's hydrogen bonding. Right. Well, you always have dispersion. So you can always say dispersion, but that's not going to give you the right answer because stuff sticks to stuff. And they're actually even the same molar mass here, pretty much. So it's hydrogen bonding is the best answer because you see an O and H's. So which one exhibits better or more efficient hydrogen bonding? C. Look at that nice OH hanging out here, right? Here you got to dig in there to get that O interaction. So this is going to have stronger hydrogen bonding. C will. So which one will have the lowest melting point then? B, because it's even weaker. Good. Okay, so you should list B first, then C. Now you got a 50-50 shot, Audrey. So it's ionic bonds, but what are the ions in KCl? K what and Cl what? What are their charges? Anybody help her? K is going to have a what charge? A +1. Cl is going to have a negative. Yeah, and 1. Just count over to the nobles. So this will be 1. And remember, the hint is also down here. They're both 1s. How about the calcium and the oxygen? Yeah, you'd think they'd both be +1 and -1 again, right? Because you just do the little ratio thing, but they canceled. Calcium's +2, oxygen's -2. Maybe that helps you. Which one's going to have a stronger interaction? A or D? The stronger interaction is going to be what sticks together stronger? +2 and -2 or +1 and -1? I would need a demonstration or something to illustrate this to you. I was hoping you could see it. These are twice as charged. They're twice as strong. +2 is, I don't know if it's twice as, yeah, no, it's going to be 4 times as strong. They magnify themselves. But +2 and -2 are going to stick together much more strongly than +1 and -1. You can pull +1 and -1 apart 4 times easier than +2 and -2. So then it'd be D and A. Good. So those are the games that you're going to be playing for the homework. Some calculations in getting unit cells, and then picking melting points. So come by if you have some questions.